live, it says. Oh, it says I'm live now. I'm alive. So I've got 3 study tables for you, which we will talk about. Once again, it's not, you shouldn't think that everything I say is going to be in the test. It's the understanding of what we're going to do, because these sorts of sessions also help you to plan for future years about, I've only just started my first sentence, to get ready for the ways that, because I teach 11 and 12, the ways to think about questions and about ways that you can use knowledge in questions. Yes?
Is all the stuff that we're doing today, is that like all the content that will be in the test?
No. There's still more to go. I just thought there was one that we did at the a few weeks ago, which was this one here, but we'll go through that again today. Yeah. There is this one here that we went through, but not, there was only like 2 or 3 people that came to that one. So we'll go through that again. And then I made this one today, which is about the different types of mining. Okay. So we can, because we've got a week or 2 before your test, we just need to make sure that we come to terms with what the knowledge is and the ways we can use it. Now, you should start to be aware that because you're coming to the end of year 8 now, a lot of your tests are going to be less about recall and more about application. So the use of knowledge rather than just saying, oh, that's a rock, that's a tree, all right? You have to start to use the knowledge to answer the question. You have to look for advantages and disadvantages. You have to look for variables that change outcomes. Because in year 9, it gets harder. And then in year 10, it gets harder. So you need to start preparing your brains for the ways to answer application questions. There's always going to be a few marks in there about recall, but that's the lowest form of knowledge that we use. We always, and the highest is evaluation. Justify your answer. Which one is best and why? Those are the sorts of things. If you ever get to the point where you're saying to yourself, oh, look, I'm off the screen. They're looking at my chin. If you ever get to the point where you think you know everything, and that's just recall, the next step you can do is start to look at advantages and disadvantages. Start to look for ways to use the knowledge. Start to look for which is the best option and why. Providing evidence, okay? And that will give you the higher order skills. And the sooner you start to do that in year 8 and then year 9, it puts you at the top of the year, because a lot of the rest of the year are happy just to keep rolling along, just knowing what they have to know, not using the knowledge. The people that get the top marks are the people that use the knowledge and can justify their choices. Okay? Sometimes there's no right or wrong answer. It's the way you justify or provide evidence to support your answer. But they're the top people. At the very top there, that is the evaluation questions, the compare and contrast questions, being able to fragment your knowledge and put it back together in a different form. They're the people that get the top marks. Okay? So we'll start with rock properties, or rock properties, mineral properties. So you need to know all of these. All right. And we'll start down the bottom there with luster. Now, luster is caused by, and I put this on my Insta the other day, it's where we get a flat surface. And when light, is it going to wibble and wobble? Have we got a wibbly wobbly board? Right. When light comes down and hits the surface and then goes away and into your eye, that's how you see things. Back in ancient times, they used to think that your eye emitted a sort of light that would hit an object and then you would see it. But we now know that light comes down from a light source like the sun, bounces off the surface and goes into your eye. And light can only travel in straight lines. Okay? So if the surface is flat, it looks shiny. This board is going to annoy me. Look at it. Okay. It looks shiny. The flatter the surface, the more mirror-like it is, the better the reflection is going to be. If the surface of the crystal is uneven, then you're going to get light dispersion. It's going to be refracted off in different directions, and it's going to look dull. Okay, so this is going to give you dull, and this is going to give you shiny. The word we use for crystals with respect to shyness is luster. Next week, remind me not to get the flippy floppy board. Okay? But luster hits the surface of the crystal. Well, the light hits the surface of the crystal, bounces off and into your eye, and the flatter the surface, the more luster it has. So things that have a lot of metal in them, and all minerals do, but the different types of metals can give you different degrees of luster. Okay? That's the first one. The second one we'll do is color, because that's quite related. Color is where we have, God, look at that board. Maybe someone can get me another board that's not so wibbly wobbly. Excuse me, librarians. Talking. I'll do it. Even though I'm on live stream. I'll get it. Take a break.
It's so mean. So whilst it is shining, it's way
Education in action. Hey!
Oh, it's too bumpy.
What's wrong? You want this to block out the sunlight for you? Right. Color. Color is where you've got a crystal, light is coming through the crystal and popping out the other side into your eye. What determines the color? What determines the color of a crystal? It's got to do with the parent rock. So what do we mean by parent rock? This is the parent rock. What do we mean by parent rock?
Original rock?
The original rock. So it hasn't, nothing's happened to it. It's the crystal. But what is it about the parent rock that determines the color?
The minerals?
Yes, the mineral. So, but that's not enough information. What is a mineral?
Like ionic compound?
Well done. It's an ionic compound. What word can we use that also starts with I that means it's an ionic compound? Do you need a clue? It means not organic. Right, if I was not capable, I'd be incapable.
Inorganic.
Inorganic. So, inorganic, which means it's going to have a metal and it's going to have non-metals. All right, and the example that I used in my class the other day was sand is silicon dioxide. Silicon is the metal, it's actually a metalloid, and oxygen is a non-metal, and that provides the bonds within that crystal provide the color. And I'm sure you've seen when if you melt glass, if you melt sand, you get glass. Yep? So it becomes see-through. Okay, but that's what gives the color. And if you're looking at a natural piece of sand that's melted, if you've ever found on the beach some melted sand, it's not completely see-through, but it's opaque. Okay, and that's what gives you your color. All right, all good there? Anyone have any questions about that idea? Because now what we're going to do is, oh gosh, I'm still moving. Oh, we're now going to crush. we're now going to crush the parent rock. Okay, when we crush a rock, it becomes,
3.
sorry,
3.
that's the characteristic, right? It's going to create the characteristic of streak, right? But it's going to be a powder. Streak is the color of the powder. Right? There are 2 ways to find out streak. One is to grind it up, and the other one is to rub it on a white surface. And the mark that's left behind is the streak. The color and the streak aren't always the same. Normally they're related to each other, but they're not always the same. Because if they were the same, you wouldn't have 2 different types of characteristic, would you? No. So the streak is what happens when you've got a much finer particle instead of the large parent rock. Don't forget, if you've got a question, just ask. You don't have to put your hand up as such. Right? We'll just have a nice discussion. Yep.
If the streak is white, would you still rub it on a white surface, or would you rub it on a black surface?
I don't know. I've never tried rubbing white rocks on black surfaces. But you would make do, I guess. You'd live on the edge. You know what they say? If you're not living on the edge, you're taking up too much room. Right. You didn't know they said that?
No.
Oh. Well, this is a less wibbly wobbly board, but now it makes noise. Right, so the next one is cleavage. Now this one requires an external force. And there is a very good external force that starts with H.
Hammer.
A hammer. Right? What will happen is the crystal will shatter. It will shatter along points of weakness. Most of the time, that weakness is not through the middle of the crystal. It's around the outsides of the crystal. Yeah? So if I just pretend if I had a brick wall, etc., and I hit it, it would go up through here, along here, and up there. It wouldn't necessarily, you'd have to hit it particularly hard to go straight through the middle of a crystal, because that's the hardest point. Okay? But cleavage has got to do with the crystalline structure and the way that the crystals lock together. All right? Force will always find the path of least resistance. Okay, so if you hit it, it will shatter along between the crystal structure. Okay, because that is where the bonds are weakest. Because these crystals here, they've got interlocking atoms. And between the crystals, there isn't that interlocking action between the different atoms. They have other ways that they are able to be joined together. All right? So the way that it shatters is called the cleavage. Some things will shatter in parallel lines, like mica, like slate. Okay, it will shatter in those nice fine layers you've got. That's how you can get slate tiles at home. Okay, whereas others will be more crystalline or more chunky crystals, and then when you hit it, it shatters into the shapes of the crystals. All good? Right. The next one is hardness. And this is named after Mo. I don't know who Mo is, but it's Mohs scale of hardness. maybe if I was a geologist, I would know who Mo is. Okay? Mohs scale of hardness. Right? It is relative or a comparison right? What happens here is you get rock or crystal number one or rock number one or mineral number one and mineral number two, and you rub them together, and the one that isn't damaged is harder than the one that is damaged. Okay, and there is a scale called Mohs scale, and the toughest, the strongest is diamond. Now, here's a why question. Here's an application question. Why is diamond? But diamond is odd because it's actually not inorganic. It's just made of carbon.
It's the strongest because it can only be scratched by another diamond.
Yes, but why? That's a descriptive thing. I want to know why it is the top. Yep.
Because the bonds are the strongest.
It's got something to do with the bonds.
The crystals bond the tightest together.
Yeah, it's actually a 3D. Instead of being 2Ds and lines, it's actually in 3 dimensions. And that is the strongest type of bonding there is in the world. The more 3D bonding you can have, the stronger the crystal structure is going to be. And diamond, because it's only made of carbon, each carbon is connected to another 4 other carbons. And so it makes this 3D network that makes it super, super strong. Then down the bottom here, at the weakest, we've got something like talc, which is flaky and in sheets. Right, you've seen talcum powder, I'm sure. You might have been sprinkled with it when you were a baby. It's very soft. You didn't have talcum powders sheet on you when you were wearing nappies? Yeah, it's very, very soft. Okay. If I got a diamond, just I had a lump of talc and I had a diamond and I rubbed the diamond on the talc, the diamond would be perfect and the talc would be destroyed. Okay. But it's a relative scale. And we've done now enough experimentation to work out what is harder than what. Okay, so you should be prepared to be able to work out a Mohs scale of hardness based upon who gets damaged and who doesn't get damaged. It's an application question.
Will it tell you which rock gets damaged by
Yeah, well, if I didn't, would it be a question?
I thought you meant you had to know the type of
No,
rock.
no, I would just tell you. I would say, and this is what I tried to do in my class, but I would say, just say Kira was rock number 1 and she rubbed up against rock number 2 and she damaged rock number 2. Which one would be harder? Kira would be harder than rock number 2. Then I've got rock number 2 and rub that against another rock. Then you can work out who's above and who's in the middle. All right, so it's just a thinking question, right? But it's applying the idea of what Mohs scale of hardness is. All good? Right. Any questions? These are just characteristics of minerals. Right, these are the physical characteristics, not the chemical, the physical characteristics. All right. Now, if we will go on to, let's go on to this one here, which is about fossils. All good? So, I would encourage you always to ask questions like why and how and when, and those sorts of questions always lead to higher order thought, right? Don't be happy with what anybody, if they've read the book, should be able to get. The thing that will separate you is, can you use the knowledge? That's the thing in years to come that's going to separate you as you're going through. And you want those top results because education gives you opportunity. You don't want to be told what you're going to be in life. You want to choose what you're going to be in life. So that education, that ability to think what you're going to do and how you're going to manipulate the knowledge gives you choice. All right? And you can always ask me a why or a how question. If I don't know, I'm only human, mostly. Okay? Half robot, maybe. My right leg, 1/4 robot. Right. So now we're going to talk about fossils. And up the top there is the process of making a fossil. All right, we've got death and decay, rapid burial, permineralization, and erosion. So we're going to first of all discuss what a fossil is. What is a fossil? Yep. Well done. Evidence of past life. Okay. It's anything that shows that something used to live. Okay, and there are different types. There is petrified. What does it mean if you're petrified? Besides being scared. When you're scared, you look like you're made of?
Bones.
No!
Stone.
Yes, you're made of rock, made of stone. All right? So petrified is when is the normal fossils that we think of, they look like they're made of rock. Yep. They can be traces which aren't part of the original organism, but more things that the organism used during its life, like a nest. Okay? So if it made a nest, you can fossilize the nest, and that would be a trace of past life. All right? And then the last one is an impression, which is like a footprint. So if the dinosaur was walking across the surface of a mud flat off Broome, they've left this track of footprints, and we can now tell that dinosaurs walked across that. We haven't found the actual bones of the dinosaur, but we've seen that they walked across that mud flat, and it's now turned to stone. Yes?
How did those footprints stay there for that long?
No one ran over the top whilst they were there.
So
We'll talk about in a minute the conditions for fossilization. Yep. Sorry? Eggs. Eggs. The egg itself might be a trace, but if you've got a baby inside the egg, there are fossils where the egg has been cracked and you can see the baby inside. And so it's like sort of like a combination. But if you just find the egg, then that would just be a trace. But I don't think we're going to ask you in year 8, tell me if it's a petrified, a trace, or an impression. They're just the ideas. All right? The process is important. The process is important. The process is the steps that is undertaken to make the fossil. So the first one is death, because it's pretty hard to make a fossil if you're not dead. Yeah. Then we get rapid burial. Now we say by sediment, but it doesn't always have to be by sediment. In sediment, we're normally talking about an aquatic environment. So it's covered with water. So the vehicle, the thing that's moving the sediment, is water. Okay? When we did Wedkirker, deposition, as it falls out of the vehicle, it gets laid down in layers, right? Normally by sediment, but it doesn't have to be. Sorry? Cast? Out of plaster?
No, like tar.
Oh, tar. Sorry, I misheard you. Yeah, like a tar pit. There are places in the world, like off Siberia and things, where they get stuff that makes roads. And if you were a woolly mammoth and you're walking along and you fell into a tar pit, it's not going to end well for you. But then in 500,000 years' time, when that somehow someone else goes in there and they pull out a woolly mammoth, the woolly mammoth is going to be fossilized, but it's not covered in sediment. It's just dehydrated because of the tar. Yeah. Same with amber, the sap that comes out of trees. There's lots of examples. if you go off to a crystal shop, you might be able to buy a piece of fossilized amber with ants in it and the ants might be hundreds of thousands of years old. Okay? So rapidly burial by sediment, but it's more the rapid burial bit that's important. Yep.
I've just got one question. If something gets frozen in ice, is that a fossil?
Yes, it is as well, because they have found woolly mammoths that were walking along the glaciers and fell down a crack and were trapped for 10,000 years. And most things don't live for 10,000 years. And again, they get dehydrated and they get fossilized. It's more the rapid removal from the environment then. Might be a better way of saying it. All right? Right. The next thing is we're going to have mineralization.
That's a big word.
It is a big word. It just means that the minerals in the water table replace the organic components. Because you are aware that things that are alive are organic, yeah? And you need to replace the organic parts with rock. And the very finest, or the most basic component of a rock is a mineral. Yeah? Anyone ever watched that show about, I think it was on last night, the opals? How the silicate water, mineralized water goes into the cracks and it forms opals. It's that sort of thing. Right? But now it's replacing organic components. Right? Permineralization means replacing the organic parts with minerals. Okay, and the minerals will then give the characteristics of the rock that it forms. Okay, and then we never know that it was there unless we've got weathering or erosion. Okay, you need to know that the fossil's been exposed to know it was there in the first place. All good. That's just the wearing. That's when we have physical, biological, and chemical weathering. Yeah, which is one of the things that some of you turned one of the questions into in the last test. Remember, I was talking about the different types of sedimentary rock, and some of you went down the path of different types of weathering. Yeah. Anyway, not to harp on it, it's just we learn from these things. We need to learn to understand what the question's asking before we can answer it properly. Yeah, and we'll get there. All right, so that's the process of making a fossil. The conditions are also important. The conditions for fossilization. One day, I'm going to get a non-squeaky board that doesn't wobble. Right. Conditions for fossilization. And we need to what this is to understand why it's important. To know that it does happen is just a recall. To know why it's important is the higher order. All right. We always now want to go for the higher order thinking, because that makes our recall look really simple. And we can smash out the recall and we can go for the top marks, what we call discriminators. In every test, there's discriminator questions that works out who's going to get the A, who's going to get the B, and who's going to get the C. The people that get the C just know what happens. The people who get the A know why it happens. That's what we want. So conditions, we want hard parts. What is a hard part of an organism?
Bones.
Bones are a good one.
Teeth.
Teeth are a good one. Claws.
Noses.
Noses. Beaks. Yeah. Talons. Anything that's hardish. Okay. Because they decompose less. And they're easier later on in life, later on in the process to have permineralization occur. Okay. Hard parts. Low oxygen. What happens if you leave something on the bench in the presence of oxygen for a week? It goes moldy and rots. Can you make a fossil out of something that is rotted? No. So low oxygen, you're reducing decay. These are the whys. Okay. What about Neutral pH. What is pH?
Put it in your pool.
Wait, wait. pH is a measure of something that starts with A. Acidity. Now, a neutral pH means it's not acidic. Why don't you want it to be acidic?
So
Because it will dissolve.
Well done. Because acid dissolves bones. Okay, and we can't make a fossil if the bones are dissolved. Yep, we want to have low disturbance. So disturbance can be man-made or anything ecological. It can be a scavenger. It can be mining. But it's hard to make a fossil if you've been eaten by a fox, isn't it? Because now you're fox poo. Yeah. It's hard to become a fossil if a machine has run you over and splattered you everywhere. Yeah. So the longer it's left undisturbed for, the better chances you have for the next one, which is lots of minerals in the water table. What process is that? What process are we allowing to happen efficiently if we've got lots of minerals in the water table? Is that fancy long word again? Permineralization. If you don't have many minerals in the water table, it's going to be very hard for you to replace any of the organic parts with minerals. So we can normally say almost like the saltier the water, the more minerals, the more inorganic stuff that's in the water, the better fossils are going to be made. We want it to have lots of dissolved minerals in it. Okay, because that allows all the organic parts to be replaced with the inorganic parts of whatever's dissolved in the water. Right? You can get fossils that are made of amethyst. You can get fossils that are made of opal. All right? They look quite fancy, but they're rare. Right? But the type of mineral that's replacing the organic parts gives the characteristic of the rock that's formed. Okay? What else can we write there? Oh, and one of the most important ones is rapid burial, because it needs to be buried for all of this to occur. So the quicker it's buried, the less likelihood that we're going to get anything else interfering with it. You tired? You had a long day. Did you have science today? No. Neither did I. Well, I didn't have year 8 science. I had 11s and 10s and 12s. It was a harder day. Right. Moving on. So now we're getting up to process conditions and that. Oh, let's do law of superposition. Now, this has got to do with the rapid burial. Law of superposition. This is about the burial of the fossil. If I've got a layer, and then another layer, and another layer, and another layer, and another layer, and another layer, which one's the oldest layer? The bottom. Old, young, that's called the law of superposition. And it just states in a rock strata is layers of rock. In rock strata, the oldest rocks are at the bottom, the youngest rocks are at the top. When would that not be right? What could occur that might change that?
Earthquake.
An earthquake, yeah. Anything that moves the rock. A fault zone, anything that could move the rock. These are the sorts of things you have to try and think outside the box. Why might it not be so? Why might it be flipped upside down?
Oh, I was going to say it got flipped upside down.
It did get flipped upside down. Well done, Jane. Right, yes. Sorry? It's anything that is able to change the original layer of the rock. So you might have had a cave, and as it fell down, it might have tipped upside down. It's anything that's reasonable. Okay, an explosion, a comet hitting, could be anything that's reasonable, as long as you could justify, as long as you can provide evidence, a reasonable amount of evidence that it might occur. All right, you wouldn't say eaten by a giant wombat. Okay, it's 2 yawns in like 2 minutes. You're being rationed yawns now. That's fair. Do you not think? Oh, you think it's a free for all for yawning? Right. So, law of superposition. Now, let's do index fossils. So, in particular layers, you're going to have a particular fossil that only, these are called index fossils now. So, in that layer, we're going to get what's called an index fossil. An index fossil is a particular fossil. It only lived for a short amount of time. All right, and in the geological time scale, we'll say 1 million years. That's in the, because how old is the Earth? What is it about? 300 years? 3,000 years?
Billion.
1 billion years? Is it 1 billion years? How old is the Earth?
4.6 billion. 4.56 billion.
Oh, maybe.
4.65. Yeah.
It's old. It's around 4.5. Say, I've been known for about 4.3 billion years. The oldest rock on Earth is about 4.2 to 4.3 billion years old. Right? We can't then tell exactly how old it is because of the rock cycle. You know, rocks keep getting changed, melted and reformed, etc. Right? But we'll say 4.2 billion years old. Okay? So 1 million years out of that 4.2 billion is relatively short, but from our perspective, it's a long time. Now, the index fossil was widespread, which means it was everywhere around the world. Okay? Widespread means everywhere. Yes? Million years. I took a shortcut. Okay? Lived for a short amount of time. Million years is short in the geological timescale. Was widespread, lived across the entire surface of the Earth, and it was common. So not only was it all around the world, but there was millions of them everywhere. You couldn't escape them. You take a step, you stand on one. You take another step, you're standing on another one. They're everywhere. They're very common. So because they're very common and everywhere, we can use them as a marker. Yep. And we can say that anything that is above this index fossil is going to be younger. Anything below the index fossil is older. Yep. Now we can compare rock strata. What did I say rock strata was before?
The layers of rock.
The layers of rock. Right. So now we can look at layers of rock from all around the world and using index fossils work out who is older and who is younger. All right? That's called the correlation of rock strata. The correlation of rock strata. So if I had, we'll keep it nice and simple. There's rock strata from one place in the world. Here is a sample. And here, there's our stars. And then here, we've got them here. All right, and we call this A, B, C, D, E, F. Yep. Correlate means to match up. And we can see because they've got the same index fossils, they must have been around at the same time. So we can go shrink, shink. Yep. So oldest to youngest. D would be the youngest. Then E. Then F and A are the same. F and A are the same. And then B and C. That's the correlation of rock strata. All good?
So it's just how
It just allows you to link up, because not everywhere in the world do you always get the same fossils, but you can work out who is going to be older and who is going to be younger based upon a known date. Okay? All good there?
Don't rub it out.
Don't rub it off. Don't rub that off.
Sorry,
Dun, 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 dun. I'm trying to finish by 4:30. It's 4:15. All right. So now we're going to do, there are two types of dating fossils. There is relative and there is absolute. Relative is if you're older or younger, like what we just did, and absolute tells you the age of the fossil. Yep. So we'll work upon absolute now, and you need to know carbon-14 dating. This is where carbon-14 is radioactive. All good? Radioactive means it decays. That's why we call radioactive decay. And as it decays, it turns into a different element. But as it decays, it releases energy. Okay? So, and the rate at which it decays is called the half-life. The half-life of carbon-14 is 5730 years. So that means that at the time of death, you've got 100% of the carbon-14 you're ever going to have. Yeah? After 5,730 years, you're going to have 50% of your carbon-14 left. After 11,460, you're going to have 25%. After 17,190, you're going to have 12.5%. Keeps going down by half. Will you ever reach zero? No. But we do get what's called a standard curve or a calibration curve. And so we draw the calibration curve like this. All right. So here, this is the percentage of carbon-14. And this is time. All right. So I can say a half-life here is 5730 years. So here I'm going to have 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Here is 100%. Here is 50. Here is 25. Here is 12.5. All right. So at the time of death, oh, look, I've changed pen color. Da, da, da. You're tired as well. Jeepers, am I keeping all of you up?
Yeah.
Sorry. So at time 0, which is it's just died, it's got 100% of the carbon-14. After 1 half-life, is that about right? We're at 50%, 5,730 years. After 11,460, we're going to have, it's hard to see sideways. There we are there. Am I getting it right? Ish. At least you got a bit of a smile. Jeepers, creepers! What a hard audience. All right, and so we end up with this standard curve. This is important. Oh, here we go. Pinky purple. All right. Oh, I was going so well. Right. Now, this we can find out the percentage of carbon-14. All right, so black. I'm very serious today. So if I said there was 35% of carbon-14 left, we can actually tell how old the fossil is. So we'd say 35 is about there. We would go across and we would go down. And because we had a really nice accurate scale, because we're using graph paper, we'd be able to tell how old the fossil was. You need this skill. Okay? This is a skill not only just in this topic, but throughout the rest of your years, you will need to, this is called interpolation, trying to find data within a data set. Yes? I told you I'm not answering those questions. I'm saying this is important information and how we use it. Yep. The reason I don't tell you what's in the test is because that's called teaching to the test, and it doesn't take any brain power at all. All right? The thing that takes brain power is using knowledge to answer questions. Murder mystery in the library with a candlestick. Yes, I know. Right.
That's funny.
Professor Mustard. Oh, Mustard! Right. Hi.
Is the one like the graph, is that relative or absolute date?
This is absolute
Okay.
because it will tell you the actual age. Okay? Relative is something is older or younger. That was correlation of rock strata. Okay? So now let's get on to the last one. The last study table. Last study table.
What's the definition of half-life?
Half-life is the time taken for the radioisotope to decay by half. Okay, and for carbon-14, that time is 5730 years. All right, now we're going to get on to our last. Yes.
Sorry, the half-life is the time taken for what?
For the radioactive element to decay by half. Okay, so now we're going to get into this one, which is about the different types of mining that you should be doing in class at the moment. All right. So the first one is mineral. How did we define mineral earlier? Remember, it was not organic.
Inorganic.
It was inorganic. Inorganic. Yep. And therefore it's ionic compound. And because it's ionic, it has a metal and a non-metal. See how you're building up knowledge there? You're not going for one word. If you just stayed with inorganic, it means very little. But now you're learning to expand the idea. That could be a 3-mark question. What is a mineral? You're not going to just say, oh, it's an inorganic thing. You build up your answer to show that you know more than other people that just know the word inorganic. Right?
How would you put that into a sentence?
A mineral is an inorganic substance that is an ionic compound made of both metals and non-metals. All good? Just layering the ideas, becoming more and more complex. This is what I try and teach my year 12s. Don't get used to saying simple things. Always build. Let the answer flow. Ore. An ore is a rock or is a parent rock. What does parent rock mean? Original rock. A parent rock.
Wait, is that an or?
That is. Or an if you want. Now I'm getting up to the bad jokes. An ore is a parent rock with a valuable mineral. Yep. If it's got something that's not valuable and you can't make a profit, it's not an ore. Okay? It must be commercially viable. Yes?
So is that why we mine ores?
Yes, because we want the valuable, we want iron, we want gold, we want silver, we want titanium, we want nickel.
And is everything called like something ore? Like,
Yes, but they have special names like bauxite. They've got, but we don't need to know those as such. We just need to know the theory of them, because once we know the theory, we can apply it to anything. Yep. Valuable mineral. That's what an ore is. Mining is extraction of ores to make a profit. Because companies won't dig up ore if they're not going to make money. They're not going to do it for fun, right? They want to make money. And they'll only make money if the ore is valuable. Okay? Mineral formation, you did that in your last test. Remember chemical sedimentary rocks?
Yeah.
The evaporation of water leaving crystals behind?
Yeah.
Yeah.
Are they
But sometimes, sorry, here we're talking about crystals, or sometimes they react with oxygen like aluminium will form Al2O3, bauxite. It will react with oxygen in the air to form a rock that you will need to get rid of the oxygen to get to the aluminium. Or iron, Fe2O3. All good? Right. Uses of minerals, we just need to think about what the mineral is. Gold, that's fairly straightforward. It's just trying to think about what you would use it for. Gold you might use in jewelry. Copper you would use in wires. Steel you would use in buildings. That's just an application, but you need to think of the property of the metal and what its properties are to give you the characteristic why you're going to use it. Okay? Then we get down to the 4 different types of mines that you need to know. Up till now. For 5 minutes. Do I? 5 minutes. Now, with these 4 types, there are advantages and disadvantages. This is one of the things a lot of people won't think about is why do we do it? We do it to get out the ore and to get out the mineral, but there's always going to be disadvantages. All right, that's one of the evaluation questions. Why would we bother? Is it worth doing it given that we know that there's disadvantages? Okay, so the first one is open cut. Now, all of these suggest that a geologist has gone along and found where there is a deposit of ore. They're not just going to dig anywhere and expect to find gold. Okay, so a geologist has gone along and done some sampling and knows there's going to be gold there. All right, open cut, you dig a big pit. In the diagram there, that's an open cut mine, and it's in levels like that. Looks like this is from side on. That allows you to drive around to find the seam of the precious ore. Okay. So the word there is seam. All right. And then we dig out that seam and there's a road there so we can access it and take it away. Yep. But the problem is there's a dirty grade hole there. That hole takes sometimes 100 years to dig. Has anyone been to the super pit in Kalgoorlie? That's massive. That's why it's called a super pit. It's taken a long time to dig. Is it going to take a long time to fill in? Yes. Are they ever going to fill it in? Maybe not. So we're always going to have a really large hole in the middle of nowhere, which could be important at some stage. All good? So that's a disadvantage. It takes a long time to mine, and you've got to fill up the hole. And the bigger the hole, the harder it's going to fill. And think about the ecosystem that was destroyed to dig that hole. Let's pretend something ever lived in Kalgoorlie in the first place. Anyone born in Kalgoorlie? Right. So that's open cut. The next one is a strip mine. A strip mine, there's 2 types of strip mine. One is that we've got an ore close to the surface. So it's easy to get to. Or the ore is above the bedrock. The bedrock is the igneous rock at the bottom and the sedimentary rock is on top. A strip mine, you take out a long strip like a road, but it can be maybe 100 meters wide. And depending if you're trying to just dig down to the surface to find something like coal, or you want to go down to the bedrock to find gold, you can end up with this rather deep hole that goes over a very long, right? And what negativity is going to be there? What happens if you go through the middle of a population of wombats, and the wombat likes to travel to see their sisters on the other side of the strip mine, but now there's a kilometre wide strip that's 30 meters deep, is the wombat going to be very happy? No,
It can't cross it.
can't cross it. What do we call that? This is biology. Oh, H and F.
Habitat.
Habitat.
Fraud.
Far,
Farming.
farming.
No. Fragmentation.
That's my next
Habitat fragmentation.
My
You're putting a big pit through the middle of an ecosystem, and what's on the one side can't reach the other side. All right? It destroys populations. Okay? Yes.
Does it mean it has to be fragmentation?
Sorry?
Does it mean that it has to be concentrated? That's this one, right?
Normally, you only dig where there is the concentrated stream. Okay? You're not gonna ever set up a mine where there's not enough percentage of ore that's to make it viable for you. Later on, next week, we'll talk about phytomining, where you've got really small amounts of ore, and there are some plants that take it up out of the soil for you. Okay, but then you've got to set fire to the tree. I know, right? So that's strip mining. Then we've got dredging. In dredging, that's aquatic. So we're talking about in riverbeds. We're talking about in river delta. We're talking about in close to the shore. Has anyone ever seen that show where they've got big excavators on the back of small ships and they're going digging up bits of dirt and putting it in and trying to get the gold out? What do you guys watch at night? Not informative stuff. You've got goggle box or something, do you? Right. Dredging, it's aquatic. It's aquatic, and you are digging up. Oh, my writing's going more erratic. Digging up ore. And then you've got to isolate the important bits. Okay? But sometimes in that diagram there, I've got a diagram there, there's a barge that's dredging up the bottom of a river, and it's pumping the sediment that it's digging up back to a little factory to extract the ore. Now, what's going to be a disadvantage there? What's going to happen to the poor waterway?
It's going to get polluted.
It's going to get polluted. What else is going to happen to the poor? What's going to happen to the fish that live in that waterway?
They die.
They could get dug
Or
up.
they get really sick.
They could get very sick. Or what happens when you dig in? Has anyone ever gone into the ocean and you've dived under the water in that 1 foot of water and then you've dug it up? What happens to the water there? It gets very murky. All right. And then fish can't see where they're going. They can't see to watch out for predators.
A shark. But then
Possibly.
Can't the shark not see either?
Sorry?
Can't the shark not see either?
I don't know. Maybe you could ask the shark.
I know.
Maybe you could go to Exmouth or Shark Bay, wait for a shark to come near you, kick up lots of sand and see if you get eaten. First-hand experience. Possible. Right, and the last one, which is the most dangerous, worse for the environment, is called in situ leaching. This is where we use chemicals that dissolve ores. All right, and the worst example is cyanide. Cyanide dissolves gold in the ground. That's also very toxic to you. If you were to touch the cyanide, you would die. Yes.
But why do they want to dissolve it?
Because it's very hard to get to. It's underground. They can't be bothered digging it up. So they're going to pump cyanide underground, and then they're going to suck up all of the liquid cyanide that has dissolved the gold underground, and then they're going to isolate it above ground.
Oh.
Does that mean that they don't need to dig a hole?
They don't need to dig a hole, but are you ever going to suck up all of the cyanide that you've pumped down the hole?
Oh.
No. So anything that lives underground is going to die. Also, we create something called a tailings dam. Tailings is where you then, once you've taken the gold out of the cyanide, you're left with the cyanide. And so you put it into a large dam full of cyanide.
Ooh.
All right, not going to be very good, because these dams invariably burst their banks, and then all this cyanide, all these toxic tailings run downstream and kill life for hundreds of kilometers. If you go home tonight and you look up burst tailings dam, there was one in the last decade in Brazil where they built this rather large tailing dam. It burst its banks and it killed everything downstream for hundreds of kilometers.
Did it kill any people?
If anyone was in the way, I don't know. I wasn't there.
What cyanide got in it that makes it so toxic?
It makes your, cellular respiration? It doesn't allow your cells to use cellular respiration.
Oh, jeez.
Therefore, you die.
Do you die like straight away if you like touch your hair?
But why?
It depends on how much you drink, I guess.
But if you like touched it, would it like burn your finger?
It wouldn't burn your finger off, but you would most likely die.
Okay,
Okay?
I won't try it.
So basically your body just stops functioning.
Yes, all of your cells stop functioning. And if your cells stop functioning, are you alive?
No.
No. Fine. Right? No, they haven't worked that out yet. They haven't worked that out. All the rich companies like Rio Tinto, BHP, Santos, they go to 30 countries where there's no regulation. And then they walk away from their mess. And then they take all the profits and they just leave the mess behind. There's no solution. Sorry?
My mum always
But now she doesn't.
My mum's got a favourite.
Have a nice day. Now feel free to yawn as often as you like.
Thank you, Mr.
All right.
Thank you.
Let's see if we know how to stop this. End stream.
No.
Right, baby.